All right, this here is the video for anyone that is making test corrections for the Chapter 7 test. And this in particular is version A up there in the corner, or right here. So if you have version B, you're on the wrong video, folks. So switch over to that one. So again, just skip ahead to the questions that you got wrong if you need help. Number one is essentially getting at the idea of, do you know what a statistic is versus a parameter? Populations produce parameters and samples produce statistics. So they're asking you what the 92% is. So did the 92%, is it describing the whole population, or is it describing a sample? And it says here that a poll conducted from the Associated Press, a poll is a sample, and samples produce statistics. Um, and it's the result of a sample. So it's not a sample itself. The sample would just be the poll. Maybe to be more particular, it could say how many people were in the poll. That would be the sample. Sample parameters, not even a thing that we talk about. The population parameter isn't even listed in this story. The population parameter would be the actual percentage of people um, that, what were they actually reading here? I forget. That said that a year from now, their family financial situation will be as good as it is today. The parameter is the actual true percentage for everybody, not just the sample. The population is is just everybody in the whole country, I guess. That's who they're concerned with. Anyway, that's probably too much for number one. Number two, this is the definition of a sampling distribution. Okay, it's the values that you get from all possible samples of a certain size. And we did this in class many times um, when we did the average height of power forwards. Every table took three samples of size 10, I think it was, or maybe it was size 5, size 10 or n being 10, maybe it was n equals 5. But all the tables took three samples of size 5. Every table added up their numbers and divided to get an average. And then we put all those dots on the board, We had these dots like this. And all of our dots were X bars. We were trying to figure out where is the true average height of power forwards. That is the definition of a sampling distribution. Number three, um, if a statistic used to estimate a parameter is such that the mean or the center of it is equal to the true value of the parameter being estimated, what is said to be true? Um, it is D, you can see there. When the center matches the parameter, that means it's unbiased. Center matches the parameter. It's unbiased. Okay. If the center does not match, then it's either overestimating or underestimating. Then it would be biased. Um, okay, that's the statistic that we're collecting would be biased. Every statistic should be random, so it's not A. Not every statistic is a proportion. Like some of them are p-hats, and some of them are x-bars, so they're not all proportions. If it was non-varying, that would mean that every single sample and every single statistic that is collected would be the same. It would not vary at all, and that's not true because samples are random. They will vary. Number four, I tried to highlight a lot of things here. It says, suppose you take a random sample of size 25, so there's n, from a population. Okay, so now they're telling us population information. So mu is 120, and the standard deviation is 15. So that's sigma, okay? And now this orange part, it throws kids off. Your sample has a mean of 115 and a standard deviation of 13.8. These are the results of just one sample, not the entire sampling distribution. This would be like up here again, remember where we did the dots for the power forwards? That would be like, hey, this dot, and I tell you about the results of this dot right here, this one lone dot. That does not tell you the distribution of all the samples. That's just talking about one little dot right there. So this is a distractor for this particular question. It's trying to just throw you off the trail. So which of the following has an average of 120 and a standard deviation of 3? Well, it's C because again, sampling distributions, what we know about them is it's the collection of many, many samples of this size. And if you have many, many samples of that size, um, and then you get the average of them, like we did with the power forwards, by definition, it will be centered at mu, and they told you what mu was. This is the population average, and the standard deviation is the sigma divided by root n, because as your sample size gets larger, your standard deviation decreases. And so the sample size was 25, so it's root 25, and 15 divided by 5 is 3. Um, so that 3 matches that, and your 120 matches that. Um, what is wrong with the other ones? It is not the distribution of the population, because the distribution of the population would be 120 and 15, and that's not that. The distribution of the sample data, um, this the sample data would be like, if I kind of keep going back to this power forward example up here, you guys each collected like 5 heights of power forwards, and they were really tall, right? It was like 70, 72 inches, 71 inches, 77, and I don't know, 70 again. The the distribution of the sample data by itself would just be what is the distribution of all these heights? That's that's not what you're doing. If you want to get to determine the mean, you would have to take these heights and get the mean of them. So it's the distribution of the mean, not just the distribution of the individual data points. So it is not that. Okay. Um, the part D, yeah, the sampling distribution of the population mean. You can't do this. The only way to get the population mean is to take every single item, every single data point in the entire population and average them out. And you can't do that. We're taking samples of 25. So it's not D. Um, and that's not E because we can make a decision. Number 5, this was on the test review. A lot of kids had trouble with this one, but the main thing is to use this formula. The main thing is that you just have to know that your trials are independent so that one is not affecting the other, so that the standard deviation of one data point has no bearing on the standard deviation of the next one. And bullet point number 1 and number 2 are both pretty much talking about the distribution being normal, which is not needed to find the standard deviation. N being greater than 30, that's the central limit theorem, that's the CLT. That's all fine and dandy, but that's not what you need. You don't need to be approximately normal. The distribution does not need to be approximately normal to find the standard deviation. 6, the central limit theorem, again, is the whole n being greater than 30 to be approximately normal. Um, and that is what A is saying. Regardless of the shape of the population's distribution. And what that means is, if you remember, you remember when we did the shooting guards? Shooting guards, you may or may not. The population of the shooting guards was skewed left. Skewed population. But it still has an average height somewhere in here. It has a mu. And if you start to take samples of sufficiently large size, your samples will be clustered right here around mu. And these samples, these dots I'm drawing, uh, if you know, most of them would be right around the line. You might have a couple here, might have a couple here, but the purple line is the sampling distribution. It will not be like the red line. if your sample is sufficiently large. So that's what A is saying, and it's kind of just rephrasing the central limit theorem. Um, the problem with B, it says regardless of the shape, okay, that's a good start, but then it says the standard deviation of the sampling distribution. That is not what the CLT is about. It's not talking about standard deviation in any way. C starts off with the same thing. It says the mean of the sampling distribution of the mean from sufficiently large samples will be equal to the mean. That is true, um, but it is just not the CLT. That's not what the CLT is saying. Okay. D, as you take larger and larger samples from a normally distributed population, again, here we're talking about standard deviation, and again, it's not talking about CLT is not for standard deviation. Um, and E, this a lot of kids picked E. They got thrown off by this. It says as you take larger and larger samples, and kids started thinking, oh, good, they're trying to talk about n being greater than 30. But read on, it says as you do that, the mean of the distribution of the sampling distribution will get closer and closer to the true mean. That's not true. As the sample gets larger, it becomes approximately normal. It does not change the mean. The mean is accurate regardless of sample size. As n goes up, variability goes down. It does not move the mean or the center. Number 7, this one about the Americans and the Canadians. They have two very similar proportions. So you are essentially, it says the variability, you're comparing them. When you see variability, you should be calculating standard deviation. Here's the purple is the generic standard deviation formula. And in blue, I've done it for the Americans. They 62%, and they're both samples were the size 1,000. And in orange, I did 0.59, which was the Canadian percentage. Um, just even writing these two out, you might be able to tell that these are not going to be exactly the same, but they're going to be very close. You could take your calculator out and just make sure, um, like this. Like that. So I got 0.015, and then the other one. You're dividing by 1,000 in both of them. So, I mean, look at that. This one's 0.155525. This one is 0.153. So, yes, they're almost the same. Okay, that's B. They're not exactly the same, but very close. 8. Um, the study is investigating the habits of samples of 16 students at her school, how much time they spend on their homework. Okay, it says suppose the parameter values, and here's your parameter. Notice these are all 45, so that doesn't help you distinguish, and sigma is 15. So sigma is 15 for one student, but we have 16 students, so you got to do the standard deviation formula, and just take the sigma of 15 and divide by the square root of your sample size. So that's 15 divided by 4, which is 3.375. So that gets rid of these two. Sigma is not unknown. We know what it is, so it's D or E. And then to determine between D and E, you do the central limit theorem, the n being greater than or equal to 30. And 16 is not greater than 30. So we cannot say it's normal. If 16 was bigger, if it was big enough, if it was larger than 30, we'd say, yeah, it's approximately normal. But we don't know that, so we cannot claim that. So we say the distribution is unknown at this time. Number 9 is really getting at a z-score. So here's your z-score formula for an average, because it told you the mean weight of olives is 7.7. Now that, if you read it and interpret that, that's mu, okay? And then it says, because it says it twice, and it says the standard deviation is 0.2 grams. So this is your sigma, okay? So let's maybe highlight. So 7.7 is what goes here, and 0.2 is what goes here. So which ones could we eliminate right there? Well, you could get rid of this one because it's not minusing 7.7. Okay, the other ones all look pretty. Oh, what's wrong with D and E? D and E are using the wrong formula entirely. They have the whole percentage in the bottom. That's only if we're doing proportions. These are not proportions. They're trying to trick you by doing 0.2, and you start to think, oh, does that mean 20%? No, okay, this is the average weight of an olive, right? So it's not those. So we're down to A or C, and the determining factor is right here, greater than. So that would be A, because this is a less than symbol. So it is not C. Oh, and the last determining thing is sample size was 3, so we divided by root 3. 10, this one is another z-score, and it's a proportion. So here's your proportion formula. It was on your green sheet. It was on your cheat sheet as well. I've kind of broken it down. So this is P. This is in a large population, 46% of all the households. That's P. In the random sample of 100 houses, okay, there's N. So I got 46% goes here. 100 goes here. So we could eliminate some right now. Um, A does not have 46% in the right spot. C does not have 46% in the right spot. D does not have 46% in the right spot. So we're down to B or E again. And once again, you can break the tie by doing the more than. More than is this because that's the right symbol. Um, so this was less than. Also, more than half. So that is telling you the p hat was 0.50. If you were to think about it as drawing your distribution, the middle of the distribution is 0.46 and 0.50 would be over here. So this should have a positive z-score, so it's 0.5 minus 0.46. All right, that's the multiple choice. Moving on. This one is, I don't know what it is about this one, threw everyone off. Can you calculate the probability that a randomly chosen freshman, I don't know how many kids wrote down, we were not given a sample size. I just don't know. Maybe I need to rewrite this as one randomly chosen freshman. So that is the sample size, folks. It was one, but one is less than 30. It does not satisfy the central limit theorem. So it says, can you calculate it? No, you can't. The sample size is way too small to be approximately normal. And then you follow it up with part B. It says, what's the shape? If the samples are now 55 freshmen, 55 is greater than 30, so the central limit theorem is satisfied. Make sure you justify your answer. Do not just say it's approximately normal. That is not enough. C, the average was given to you. Okay, right there. It says, yeah, found that the time and hours that a freshman uses to study with a mean of 7.2. So piece of cake. This one is just a reminder that you have to divide by sigma divided by the square of the sample size, and the sample size was 55, and the 5.3 was right there. Now, part D, you are using the information you just found, right? So 7.2, that would be the center of this curve. That would be 7.2. And then you want to know what's the probability that someone was above 9 hours. So 9 hours would be like over here. So you should know right away this should be a positive z-score. So you're going to do your 9 minus 7.2. and you divide by your standard deviation, which you just found right there. We had that formula back here as well, right? Right here. Okay, you could use that. That was on your cheat sheet as well. Now, when you do this, if you look this up on the green packet gives you this number. But be careful, it said greater than. So again, there's that greater than symbol. Now, the green packet, I had some kids just leave it as 0.941. So you have to do, you want this side, so you have to do 1 minus 0.941. If you want to do the normal CDF button, you sure can. This is a z-score of 2.52, and you keep going all the way to 99 when you plug it into your calculator. This will give you exactly the 0.0059. When you do the normal CDF button, it gives you exactly what you're looking for. It gives you the region you're asking for. Okay, 12. Now we're switching gears. These are proportions, so now these are all P's and P hats, okay? We're talking about flipping a coin. It says assume the coin is fair, so the average proportion would be 50%. Um, and then you put a 50% there. I guess I shortcutted this a little. This would be 1 minus 0.50, but hey, that's 0.50. And it said in 50 flips. So N is 50, and a lot of you got this one, did this one well, okay? So we found that's the center and that's the standard deviation. B, when this did not go well, explain why you can use the formula for standard deviation. You guys, this was on the multiple choice. I only made this 1 point, so it didn't hopefully impact your grades as much as it could have. The trials need to be independent. If I flash back up here real quick, it was this question right here, right? The trials must be independent to determine, and here it is, the sample size has to be less than 10% of the population. So that's what they were getting at on this question, all right, right here. And 50 flips is far less than 10% of all the possible coin flips. Or you could also just make a statement that all coin flips are independent, which is fairly common knowledge. Like one coin flip has no bearing on the next coin flip. Okay. C, you're using your answers from part A right here to find a z-score and investigate this. You flipped the coin, you're playing around with it, you flipped it 50 times and you got 30 heads. Right up here, we were flipping it 50 times. So we are going to use what we found. We found up top that the average is 0.50, and we found up top that the standard deviation is 0.071. Now this is the p hat, right? 30 out of 50 is 0.60. So on my curve, I want to know how likely is it to get this result or higher. Okay, 50% is the most common result if the coin is fair. So I found my z-score, which 0.60 minus 0.50 divided by my standard deviation from up here. And what I found is that is a z-score of 1.41. 1.41 to 99 if you want to do your normal CDF button, okay? And you'll get 7.93. So this shaded area is 7.93. So let me read what this means in red before I actually answer the question. What we just found is that if the coin is actually fair, if P is 50%, if the coin is fair, then a result of 30 heads or more will only occur randomly about 7.9% of the time in samples of 50 flips. So it's not going to happen that often, okay? But since our usual cutoff is 5% and 7.9 is a little bit above that, it's close. It's not a significant enough result to risk insulting your friend. Now, if some of you said on your test, nah, I'm not comfortable with this, to me 7.9% a pretty low probability of occurrence. I gave you credit for this, but the main idea is if we were further over here on this blue line, and this probability to the right was like 2 or 3%, then I'd be really confident that this coin, something's up with this coin. All right, last question. Um, so a couple things about this one. So the 5 number summary for the number of texts per day is for the population. So this purple box is data of the entire population, and they found the 5 number summary. So we know the population's median is 55. We know the largest number in the population is 250. We know the first quartile of the entire population is 20. So now we take random samples of size 32 and we calculate Q1 for each of them. So the purpose of the sampling was to determine Q1 of the population, okay? We know from up here it is 20, okay? So we could have done this in class again with, I could have each of you take samples of like, I don't know, 5 or 10, and I could say, everybody find Q1 of your sample, and then everybody go put a dot on the board. And you guys would start putting your dots on the board, okay? So this is part A. What does the dot at 35 represent? That's this dot. Each dot, remember, each dot is the result of one sample. And you could even say sample of size 32. Okay? But more than that, I had a lot of students write, it was the mean of one sample. Like the mean of a sample, or the, not mean of a sample, or median of a sample. No, 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 no. What were they recording? What was the purpose? They were trying to determine Q1, okay? So this dot means that one of the samples had, it was Q1 of a random sample of 32 teenagers. Just one of the samples, okay? Okay, then the last one. Is the sample Q1, is this distribution unbiased? Does it have an unbiased estimation of the population Q1? We talked about this earlier up as well. It's to be unbiased, you look at one thing and one thing only. Is the center of this accurately pointing us to what it's telling us it should be? We know it should be 20, okay? Because we were told the population data, we were told the Q1 of the population is 20, okay? So what I did here is it says there's 50 samples. So 50 divided by 2 is 25. So I took my time and I went 1, 2, 3, 4, blah, 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 blah. And then I actually, to be careful, I did it from the other side. I went 1, 2, 3, 4, 5, 6, 7, 8, 25 in. And I got these 2 dots. And so the median would be probably like, that line right there in between them. Either way, this is 20. So the median, okay, um, the median or the center of the sampling distribution right here is 20, which matches the parameter exactly, which suggests that it's unbiased, okay? Other things that throw you off the scent, some of you looked at this and you said, look, it's kind of skewed right. Yes, it is, but the shape does not make it unbiased. What makes it unbiased is if the center is in the wrong place. Some of you also said, this is way too spread out. You were talking about variability. The variability of this does not determine if it's biased or unbiased. We would like it to have low variability. We would like it to be tighter like this, but that doesn't make it unbiased. So all that matters is the center of this distribution pointing us to the number we're trying to find, and it really does this time. All right, folks. Thank you. Hope that helped you with your corrections.